Okay. So we're actually starting ring theory today. What is a ring? Well, you know what a group is, right? It's a place or a set of things where you have one operation on it, like the integers under addition. But there's other ways to combine integers, right? You can multiply them, right? And this is true for lots of things that you've probably seen. If you have a collection of matrices, you can add them and you can multiply them. A ring is basically another structure where we can add and multiply. So let R be a commutative ring. That means multiplication, doesn't matter what order you do it in, with identity. And let X and Y be nilpotent elements. What's a nilpotent? That means it's an element when you take a high enough power of it, it'll get zero. Show that if X plus Y and X, show that X plus Y and X, Y are also nilpotent. So if there's a power of X that gets you zero and a power of Y that gets you zero, there's a power of X plus Y and a power of XY that gives you zero. Show that if U is a unit, that is an invertible element, and X is nilpotent, then U plus X is a unit. And show that if R is not commutative, so if order of multiplication matters, none of the above is necessarily true. Number two, let R be a ring. We say the characteristic of R is the smallest natural number, such that when you add anything in the ring to itself n times, you get zero. Sort of like the order of a group in a certain sense. Show that if R has an identity, a multiplicative identity, then the characteristic of R is n if and only if n times the identity is zero and n is minimal with respect to this property. And show that if R is an integral domain, then the characteristic of R is either zero or a positive prime. Number three, we say that 1R, respectively 1L, is a right identity if X times 1 is X. So whenever you multiply X on the right by this, you get X back for all X and T. Give an example of a ring that has a right identity but no left identity. I would look at sub rings of matrix rings for this one. Number three, any of you that have ever tutored somebody in algebra or, this is called the freshman's dream. Show that if R is a commutative ring with 1 and the characteristic of R is P, where P is prime, then to take the power of A plus B to the P to the n power, you just take the power of both ends, right? Don't you wish that always worked? And that's why this is called the freshman's dream. We define a ring to be Boolean if X squared equals X for every X in R. Show that any Boolean ring, and some of you may have seen this, anybody had any kind of computer science course we talk about, this comes up a lot in this and engineering as well, electrical engineering. A Boolean ring is always commutative and has characteristic 2. This next problem is just for fun. You don't need to turn it in. But if you want to play, it gives you some good sort of exercise into how to deal with the ring theoretic properties. Suppose you have a ring R that has a property that for all non-zero elements of R, there's a unique B in R such that ABA equals A. Prove the following. Number one, R has no non-zero zero divisors. Number two, BAB equals B, sort of the mirror image of that. Number C, R has an identity. And number D, R is sufficient, which I'll tell you about that momentarily. Okay, any questions on that? So as promised, today we're going to be talking about something called a ring. And what is a ring? A ring is basically the next step up from what a group is. So what you're used to is a group, which is just a non-empty set that's got a couple of binary operations on it that follow some rules. A ring A ring is a non-empty set that has two binary operations. Let me get right to the definition. It's not 8, it's 9. A ring is a non-empty set. Sometimes I write this way to emphasize that it's got two binary operations. This is and actually I'm not going to have to really say non-empty because in fact it's a group here. Two binary. We call this usually plus or multiplication and addition, such that number one, under the operation of addition, R is an abelian group. Okay, so this is an old familiar friend here. Number two, the operation that I'm referring to as multiplication must be associative. So I will make that clear here. This what I mean by that is for all A, B, C in the ring, A times B times C is A times B times C. So I've got an associative operation here. And usually once we get going with this, I won't even bother to put the dot. I'll just denote multiplication by juxtaposition. And the last thing that I need, by the way, anybody, so, all right, so I've got these two binary operations. Plus is an abelian group, so that says a lot. There's actually more than that. It says that plus is associative. It says that there's an identity, a plus identity. I'll call it zero, that when you add to everything. And also it means that this every element has a negative, right? Because it has to have an additive inverse. That's all I'm saying about the multiplication. I don't have to have inverses. Okay? And I don't have to have an identity like I do with the plus. Now, most rings that we're going to deal with in this class will have an identity, but usually not inverse, not multiple inverses. Now, basically what we have here is this binary operation is doing its own thing. And this binary operation is doing its own thing. I got to do something to bring them together, right? Because in a ring, these two binary operations, they've got to play together. And I want to make sure that they play nice. And by playing nice means the distributive property. So for all A, B, C, and R, I want A times B plus C is equal to A times B plus K times C. And actually at this juncture, to do it right, if I really want to do it right, I need to tell you something else. And what's that? Is that distributive property going to be good enough? That distributive property assumes that I take my A and multiply it on the left side of the B plus C. I need to talk about what happens. What if I multiply it on the other side, B plus C? So I want this to be satisfied too. So this last one is called distributive property. So here are some adjectives that I can add to this. Additionally, so this is a ring. Let's see, 4. We say R is commutative, so this is the car, these are the options. It doesn't, a ring doesn't have to have these, but, it's nice if it does. We say R is commutative if A, B equals B, A, for all A and B in R. And number two, or oh, five, sorry, say R has identity or is with identity. Identity, when you talk about a ring, usually refers to a multiplicative identity because the ring is an abelian group. It's always got an additive identity. If there exists one, sometimes I'll say one R to emphasize in R, such that X times one R times X equals X for all X and R. Now, I will tell you that most of what we're going to do will pick up both of these options, right? Although this one is the more common. Some of the rings we will consider, I might consider neither option. This option almost always applies, and this one will very frequently apply to what we study here. Okay, so examples. Always important to have examples. Z is a commutative ring with one. That's going to be my abbreviation. I don't. CRW1 means commutative ring with identity. So notice Z is an abelian group under addition. It's got an associative multiplication. It satisfies the distributive property, so it's good to go. Additionally, the order of multiplication in the integers does not matter. 2 times 3, 3 times 2, same thing. And 1 is the multiplicative identity. Yes?
What's the difference between saying R is commutative versus saying R is abelian?
Tradition and terminology.
Okay.
Abelian is usually reserved for a group, right? But a commutative means the multiplicative structure for any. Yes.
The property on 3, all those terms are equal, right? Because it's abelian for addition.
But on
Oh, wait,
3,
A, B, sorry. A, B, and A, C, never mind.
I didn't do this right. Right. Here's an observation that I think this may address what you're talking about. If you have option 4, so that is the ring is commutative, then you only need one of these, right? This one, if the ring is commutative, then you can derive this one from this one. So you only need one of the distributive options. But this covers your bases in case the ring is not commutative, right? Did that address what you were asking? How about a finite ring? How about this? Z mod n. We're used to using Z mod n. We're used to using Z mod n as a group, right? It's just additive. But you can certainly multiply in the same way. Everybody agree? In fact, let me take apart Z mod n. Let me look at a couple of examples that are kind of telling, and you can see some interesting things that happen after rings sometimes. So, example. Now, we all know how to add these because we played around, but the multiplication essentially works in the same spirit, right? So for example, in Z mod 5, somebody tell me what is 2 bar times 4 bar?
Bar.
Very good, right. 2 times 4 is 8, and then mod 5, that's 3. Everybody okay with that? In Z6, what is 2 bar times 3 bar?
0 bar.
Okay, that's something that's maybe you're not used to as much. Because you know, one of the basic things that you do when you're in like high school algebra is you solve polynomials, right? And you factor a polynomial, you get x minus 1 times x minus 2 equals 0. And what do you conclude from that? That one of those two things is 0. You say, oh, the solutions are x equals 1 or x equals 2, right? Notice the product of these two elements. These two are non-zero elements of the ring. The product is 0 anyway, right? This can happen. Notice this cannot happen here, as a matter of fact, right? Because if you multiply any two non-zero elements, you don't get 0. What do you suppose prevents that from happening here as opposed to here? Very good, very good. Notice that 6 is not prime, and I took advantage of that because 6 is essentially 0, which is 2 times 3. You can't play that game up here. In fact, this one, if a times b equals 0 up here, then one of them has to be 0, but not here. It gets worse. Here's an example. Can somebody give me an example of a ring that is not commutative? Come on, y'all must still be paying those therapy bills from 3110, right? Everybody hates the matrices, right? What's one of the big things in 3110 is matrix multiplication doesn't always work the same both directions, right? So here's an example. And I'll keep it modest for now. So this is the set of 2 by 2 matrices over the real numbers. This is an abelian group under addition because adding matrices, the order doesn't matter, right? The identity is the 0 matrix, et cetera, et cetera. And we know how to multiply, right? The multiplication of matrices is associative. You might have proved that in 3110. If not, it actually follows from what you might have known in 3190, where you learn that function composition is associative. And matrices are basically linear maps on vector spaces. So you've got associativity. You probably also observed, at least in 3110, that matrix multiplication is distributive. But this is not commutative. So this is it has identity. Somebody tell me what the multiplicative identity of this ring is? Yeah, the identity matrix with ones on the diagonal and zeros elsewhere. Like that. But it's not commutative. Right? So notice that I'm gonna have to get really unlucky for this not to work. If I multiply this way, I get 5, and why did I do this myself? 18 to 7. But if I multiply it the other way, I get, whoops, 1, 1, 4, 2, 3, 1, 1. This is equal to 5 and 6. Actually, I kind of got lucky that I matched up on the first one. 5, 6, 6, 7, I guess. My goodness, I chose determinant one, that's crazy. But anyway, this is not, these are not equal, so the ring is not good. Now, check this out. For alpha singular. How many matrices are there of this form? Infinitely many, one for each real number. Everybody agree with that? Now notice 0 alpha 0 0 0 alpha 0 0 is 0 0 0 0, which is the multiplicative identity here. So the equation e squared equals 0 has infinitely many solutions. And this ring.
X squared equals 0.
Either one, right? I chose the variable t here just because I had called this x, but yeah, so there's infinite, in fact, uncountably infinitely many solutions to this equation. And of course, how many equations? So if I gave you a polynomial with real coefficients and it's quadratic, how many solutions would you expect it has? Yeah, at most two, right? I mean, it might have two complex conjugate solutions, or it might have a double root, but there's no more than two. Everybody agree with that? But here, we can see that in these mathematical structures, sometimes what you're used to is a little bit different here. There are other rings. So let me give you another kind of large class of examples. And we'll talk more about this kind later. Example, if R is a ring, well, actually, we'll say a commutative one. I can also do this more generally, but let's do this now. So is Rx this is a set of all polynomials that have coefficients in R. What happens if I take two polynomials and their coefficients are in R? When I put them together, their coefficients are sums of things in R, which is still in R. And you multiply polynomials the way you're used to. You kind of match the degrees, right? This forms a ring. The identity is the element 1 from R, the degree 0 polynomial 1. Actually, and so is the ring of formal powers theory. Do not let this confuse you with, now, two, these are just symbols. Nobody's trying to plug in anything for X. That's where analysts make their mistake. These are just infinite. They're sort of like infinite polynomials. You treat them as symbols and add them and multiply them this way. These are another way you can build rings from. So if I walk up to you on the street and have a ring, you can build several other rings from that. You can build a direct product of rings similar to what we did with groups, and we'll talk about that later. You can build a polynomial ring, you can build a power series ring, you can build a matrix ring. Yes.
Sorry, is the difference between those two that the second one is infinite, the first one has to be finite?
Correct.
Okay, thank you.
Correct. Okay. Here is kind of the first big result from ring theory that kind of ties everything together. So theorem, oh, binomial. And you actually have all, I promise you, you have all seen the binomial theorem, at least in the specific context of the real numbers. I'm going to couch the binomial theorem a little bit more generally in terms of, well, a more general ring. What are a commutative ring? One is not really necessary. And then in the natural numbers, well, X, Y in R and in the natural numbers. Then X plus Y to the n power is the sum of X to the, let's see, n minus K, Y to the K. Where, here's a reminder. That's supposed to be a capital there. Where n, choose K. Anybody remember what this animal is?
N factorial over k factorial and k factorial.
That is correct. Good, thank you. And probably in 3190 or some such, you all probably prove that this is in fact an integer, right? Or it's implicit in this way. This is also another way that's kind of, if you prove this, you prove it's an integer as well. This is the number of ways that you can select K objects from a set of n, right? It's the number of different subsets of size K, right? So for example, if n was 10 and K is 2, how many subsets of size 2 are there from that set of 10 elements? How many of you have seen the binomial theorem, at least for the real numbers or something like that? The proof is essentially the same, right? And I will skip this. This can be done by induction. Or counting. Notice that what you're doing when you multiply this, so I'll just kind of talk you through this intuitively. If you take this to the nth power, when you're multiplying this out, every time you go through, you're selecting an X and a Y, right? So if I've got 3 of these in a row, it might be X, X, Y, and that'll give you an X, X, Y term, or it might be X, Y, Y, or it might be X, Y, X, or Y, X, Y, however it is. So what are you doing? This means that when you collect the terms, the powers of X plus Y have to add up to the same thing. Everybody agree with that? That's why it looks like this here. Everybody okay so far? Now, where does this come from? Well, to get this particular term out of my n of these things in a row, I have to choose Y exactly K times, right? How many ways? So I might pick Y as the first K times, and the rest of the time I got to pick X. Or I might pick Y, X, Y, X until I picked Y K times and the rest of them X. Or I might pick Y, the last K of them, and the first one's X, right? How many ways can I do that? That's the number of ways. I'm picking my case, my subset of KYs from the set of n things in the product. So that's another way to choose as well. Like I said, you might try to prove this by induction. It's kind of fun. You need to, and it'll kind of exercise you with some of the properties of binomial. So, and of course, this is where things come from. The famous Pascal's triangle, which you may have seen. So, for example, X plus Y squared, this is x squared plus two xy plus y squared. X plus y cubed is x cubed plus three x squared y plus three x y squared plus y cubed and so forth and so on, right? Do you all see why commutative is important here? Right, because picking these, because if you have in the non-commutative case, the only thing that you can say here is x plus y times x plus y is x squared plus xy plus yx plus y squared. If the ring's not commutative, these two might not be the same thing. You might not be able to group it like that. Are you okay with that? Okay. Any questions or any questions on that? Okay, so let me give you kind of a first collection of properties, kind of basics that you would expect to happen in a ring. And I suspect you won't be too shocked by any of this, but we'll go through it anyway. Let R be a ring. Just one of these new animals we've got. Number one. What do you hope happens when you multiply anything by zero? Yay, and that's what happens. This is something that's like really basic, right? But it's like, if I ask you to prove it, a lot of people say, oh my God, where do I start? We'll see why that's true in a moment. Minus A, given any element of the ring, it's got an additive inverse. Minus A times B is the same thing as A times minus B, which is the same thing as minus AB. For all A, B, and R. I guess here I should have said for all A and R. Number three. Negative A times negative B is equal to, what do you hope? So do I. That's actually what happens for all A, B, and R. Number four. If R has identity one, then it is unique. And minus one times A is minus A for all A and R. Okay, so finally five, if M right, if M N are in C and R S are in R, then MR times NS is MN RS. Now, I think I probably need to explain a little bit about what do I mean by MR and by extension NS. Well, so for clarity on five, hopefully, MR is equal to R plus R plus R M times. If M is greater than 0. This is equal to 0 if M equals 0. And it's negative R plus R plus R. This is the absolute value of M times. If M is less than 0. So basically, this is just how to add it to itself a certain number of times. And and what do I mean by adding a negative? If it just add the negative to itself. Okay. Let's proof some of this. Well, before we stampede off, any questions so far? Okay. One. Uh, yeah. Look at 0 times A equals 0 times A. This is by the distributive property, right? Because remember, the addition and multiplication have to play well together. And this is 0 times A, because that thing is just a big fat 0 by itself. So now I have, this is an element group. Bill plus Bill is Bill. So 0 times A is 0. So that proves that 0 times A is 0. To prove A times 0 is 0, it's the same thing, just put A on the other side. That's it. Okay. Number 2. Negative A times B plus B. So if I look at negative A times B plus A times B, again, I'm going to do the distributive property. I can write this as negative A plus A times B. Basically, I can pull a B out of that side, right? But this is 0, which by the previous part we know is 0. So what does this give me? This gives me negative A times B plus A times B is 0. Now move this over to the other side. In other words, add the additive inverse of AB to this, make it negative A times B is equal to negative. So that shows this is equal to this. The proof that this equals this is almost the same. Am I okay so far? How about this one? One way to do this, I guess. Let's try to apply the previous one. Negative A times negative B is negative A times negative B. That's by using the previous one, right? And this is negative Again, using the previous one, this is negative AB. So this is AB's additive inverse, which is AB. I'll let you see if you can get through 4 and 5. They're not too difficult. And they're fun. Any questions so far? Okay, so one of the things that's important, in part of ring theory is probably this is even more true for ring theory than for group theory, is certain elements in a ring have properties of certain importance. And so oftentimes these elements that have certain properties that are good or bad are useful. And so I'm going to tell you what some of these properties are. And you saw some of them probably a little bit when I talked about the homework today. You probably heard the word nilpotent and unit. So we'll see how some of these crop up here. Definition. Let R be a ring and A an element in R. Number one, we say A is a left respectively right zero divisor if there exists a non-zero, that's important, B and R such that A, B equals 0, respectively, B, A equals 0. So let me explain what I've said so far. We say that A is a left zero divisor. If I can hit a non-zero element on the left with it and get 0. I say it's a right zero divisor if I can hit a non-zero B on the right with it and get 0. We say that A is a zero divisor. A is a zero divisor. If A is both a left and right zero divisor. Okay, and let me make clear, because there is a point of potential confusion here. So let me tell you what it means to be a zero divisor. That is, there exists B, C, and R, not 0, such that A, B equals 0 and C, A equals 0. So just because AB is 0 and A is a zero divisor does not necessarily mean that BA is 0, but there is some other non-zero C such that CA is 0. Okay, so this is what it means to be a zero divisor. Every ring, okay, so here's the dumbest ring in the world. Can anybody give me what's the dumbest ring in the world? Probably the adjective dumb is not very well defined, but yes. Technically, you're right. Yes, that's the 0 ring. It consists only of 0, right? That's a ring, right? Because it's a trivial abelian group and the multiplication is silly. But if you have a non-zero ring, that is a ring that has something other than 0 in it, you've always got a zero divisor. What is it? zero is always a zero divisor. Because if you hit any non-zero element with it, you're gonna get zero, right? So that's something good to keep in mind. That if you have a non-zero ring, zero is always a zero divisor. Now, in a lot of rings that you're used to, for example, the integers, zero is the only zero divisor, right? Because if you multiply two integers and you get zero, what must be the case?
One, zero.
One of them has to be zero, that's right. Okay. We say, this next one is sort of like, a zero divisor on steroids. Two, A in R is nilpotent if A to the N is zero. Notice that zero is clearly nilpotent. And any non-zero element that satisfies this is a zero divisor. Because if A to the N is zero, then A times A to the N minus one is zero. And three, here's kind of the other end of the spectrum on this. We say that you, right, yeah, we need one in R. If R is a ring one, we say U in R is a unit if there exists a V in R such that UV equals VU equals one. So a unit in a ring is one that is multiplicatively invertible. Can anybody identify the units in the ring Z, the ordinary integers? Well, in any ring with identity, there's always at least one unit, and that is the identity itself, right? Because it is its own inverse. But actually, the ordinary integers has two units. One and negative one. Those are the two units. And the rational numbers is a ring. What are the units in the rational numbers? Everything except for
Zero.
everything except for zero is a unit in the rational numbers. Right. So what are the units? What are the units in 2x2 matrices over the reals? That's right. Exactly, GL2R, the 2x2 invertible matrices. Example, Z6, I'm going to classify some stuff. Actually, I'm going to go Z12. So you should look this over. For this one, so check me on this. The units are 1, 5, 7, and 11. There are actually 4 units in this one. Nilpotents, well, zero divisors everything else. 0, 2, 3, 4, 6, 8, 9, 10. And the nilpotents, in this case, are 0 and 6. Yes.
Why are the zero divisors just everything else?
That is a great question. I knew that quickly because this ring is finite. It turns out in a finite ring, every element is either a unit or a zero divisor, and we will prove that later. But notice the units, what do you see in common? What is true about the numbers that turn up as units? What do they have in common? They're, yeah, but you got a little lucky. There's something a little bit more general. They're relatively prime to 12. They've got no common factor with 12. Notice every one of these zero divisors has a shared factor with 12, and that's what makes it. And what's special about 6? What are the primes that divide 12? 2 and 3 are the only ones. These are the elements that are divisible by both 2 and 3. So that's it. We're going to discover later that in fact the units form a group under multiplication, a subgroup of this. And that's it for today. If you all really want to get your spring break started off well, we've got the math club today. Other than that, I hope you guys have a great spring break and enjoy yourself, and we will see you when you get back.